Okay, great. So hopefully the recording will turn out, and then I'll post it on my YouTube channel, and that'll be permanent. So you can watch that anytime this semester. And then it'll be available on a different source up in the cloud, I believe, for like 7 days or so. And then what I'll do is the notes from this class, I will actually post on ELC too. All right, great. All right, so I want to start out with the problem that I left off with in class on Wednesday. And so let's start off with this question. So the question is, give an estimate of the integral of 0 to 1 of 1 over x squared plus 1 dx. All right, so this is a definite integral. It represents an area, perhaps. Sorry, I have to admit a few more people, so I may stop for a second just to admit people. All right, and so so this is going to represent an area, and let's kind of draw the graph first. So here's x and y. So this function 1 over x squared plus 1, this is always going to be, it's always going to be positive. And at 0, the function is 1. And it's just going to kind of curve up here, and it's going to asymptotically go to the x-axis when I make x go to infinity, and asymptotically go to the x-axis when x goes to minus infinity. All right, now let's figure out where we're at. So we're at 0 and we're at 1, let's say. And so the definite integral will represent the area underneath this curve, all right? So let's just find an upper and lower bound for how big this area could be. So one way to do this is we can look at this function, and we could actually see that it's actually decreasing on the interval. So f of x equals 1 over x squared plus 1 is actually a decreasing function on the interval from 0 to 1. All right. So the lowest point of the function occurs at this endpoint over here. So what I can do is I can estimate using a rectangle. Let me make this a different color. So we'll make it red. So I can estimate it using this rectangle over here. So notice the area of the rectangle is always going to be smaller than the area underneath the curve because I picked the lowest point. So what is the area of that rectangle? Let's call it little m. So the height is going to be the function value of 1, which is 1/2. So the area is going to be 1/2 times 1, which is 1/2. Okay, so that's the smallest the area could be. It probably isn't a good estimate, but it's actually an estimate for a lower bound. How can we get an estimate for an upper bound for the area? Anyone want to answer? They can unmute. Or put an answer in the chat.
You do a rectangle above the previous one, it would just be an overestimate.
Yes, that's exactly right. So we want to actually use the left endpoint, and let's overestimate it. So we use this point up here, and we use this rectangle over here like this. Okay, so this rectangle goes all the way down and around like that, okay? All right, so let's call that capital M. So capital M will be sort of an estimate, and the width is going to be 1, the height is 1, so the area is going to be 1 also. So what we can say is that the integral from 0 to 1 of 1 over x squared plus 1 dx, at least it's between 1 and a half. Okay, so that gives us an estimate of what the area is. Kind of a cheap estimate in some sense. Now, to get a better estimate, what I can do is I could subdivide this in a, the area, the region or this interval in half. And then I could take another Riemann sum by using 2 other rectangles. And once I do that, I would get a better estimate. Okay, and then or else I can take a subdivision with 3 and I could do the same sort of deal. Okay, but so I'll leave that as an exercise if you want to try doing that. Okay, so you can actually estimate the area by using, areas of rectangles. All right. So the next concept I want to review is the idea of average value. Okay, so let's do that next. Okay, so it turns out if I want to find, so here's a function f over here. It's on the interval from a to b. And I want to know what values or what the average value of the function that it takes on this interval from a to b. Okay, so I'm sort of continuously averaging. So then the average value is going to be equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, so you take the definite integral and you divide by the length of the interval. Okay? So this is the average value. All right, so let's do an example. So find the average value of f of x being equal to x squared minus x on the interval from -2 to 1. Okay, so we want to find the average value of this function, x squared minus x, on the interval from -2 to 1. Okay, so what we do is we just plug things in, right? So the average value is 1 over b minus a. So a here is -2 and b here is 1, right? So 1 minus -2 is 3. Okay. And where are we integrating from? We're integrating from -2 to 1 of x squared minus x dx. All right. Sorry, I got more people in the waiting room here. Okay. Next time, I'll if I have to do this ever again, I will make sure I sort of deactivate this waiting room process.
I have a question.
Sure, go ahead.
Where did the 1/3 come from?
Oh, it came from b minus a, right?
Oh, okay, yeah, makes
Yeah,
sense.
so b minus a is actually 3, right? So
And you multiply those two together, is that what you're doing?
yeah, that's right. So this
Okay.
is multiplied. Okay.
Right, cool.
All right, good. And so now what you do is you just integrate this, and we know how to do this, right? We just take the antiderivative. So we just have 1 over 3, and we're going to do x cubed over 3 minus x squared over 2. Yeah. And we're going to evaluate from -2 to 1. Okay. And you just now plug values in. So 1/3. So the evaluate at 1, you get 1/3 minus 1/2. Minus, do it again, 1/3. And then I plug in -2 into here, so I get -8 over 3. Plug that in -4 over 2. Okay. And then I'll let you do the simplification, and eventually you're gonna get 4/3. Okay, so you can make a common denominator and simplify, and then you get 4/3. Okay, any questions on this? Good. All right, so that's an example of average value. Okay, so I kind of have like a list of things to do because this is kind of a review of some of the things you learned in your previous calculus class. All right, so the next thing we want to do before we head into substitution is I want to review formulas for antiderivatives. Okay. All right, so let's review formulas for the antiderivatives. So the first formula I'm going to start out with is the really basic formula in terms of a power of a polynomial. So I don't know if I should number these or not. No, let's not number them. So the integral of x to the n dx. All right. So what's the rule for doing this? So the rule is you add 1 to the power, and then you divide by the new power. Okay. Now, is there a problem here in terms of like when we can do this?
When the function is in the denominator, unless you like
So
bring it
the-
up to the numerator.
Well, the thing is, look at the denominator, n plus 1. Is there a value for which we cannot do this?
-1.
Yeah, -1. So as long as n is not -1, this formula is valid. Oh, good. Someone said this in the chat too. Good. So this formula is good as long as n is not -1. But when n is -1, we have a different answer, right? So what's the answer in this case?
ln.
ln, very good. So this is the natural log of x plus c. Okay, so this gives you formulas for any power you want. All right. But you have to be careful when n is -1 because you get natural log. So I don't know if you've heard the old calculus joke. What's the integral of 1 over Cavan? Anyway, log Cavan, right? So that's a way to remember it. Okay, so that's that. Those are the famous those are the formulas for we're looking at powers of polynomials. So now we can look at certain trigonometric functions. Actually, let me just do this one next. This is easy. If I just do the exponential e to the x, this is e to the x plus c. All right, so if you take the exponential e to the x, you just get e to the x back again. So the integral of sine of x. So what's the antiderivative of sine?
It's a negative cosine.
Negative cosine, right? Good. And the derivative of cosine is sine of x. All right, so there's kind of a relationship here. I mean, if you know one, you kind of know the other. Because what you do is you take the answer, you it, and you put a minus sign on it. So if I want to know the integral of cosine, right, I know the integral sine is minus cosine. So you the cosine, so you get sine, and then you put a negative, so you just get sine of x. So that's kind of the general formula or idea. Okay, so what about the secant square root of x?
It's a tangent.
Okay, good, tangent. Okay, so let me just make sure my pen has enough juice in it. Okay. And now when I do cosecant square root of x, well, let's use the rule, right? You the tan and you put a negative sign. Okay, does everyone kind of get that? So if you know secant squared x and you forget on what's cosecant x, just the tan and put a negative sign on there. Okay. All right. Now if I take the integral of secant x, tangent x, I get secant x. And then if I want to take the cosecant of x, the cotangent of x dx, well, same deal, right? You just the secant and then put a negative sign. All right, so these are formulas that you should have derived from your first semester calculus class. Now, the ones which are a little bit more esoteric are if you take 1 over the square root of 1 minus x squared, you get the inverse sign, right? So the arc sine of x plus c, and the integral of 1 over 1 plus x squared dx. So what's the antiderivative here?
Or cosine.
Well, I was kind of giving an answer.
This was tangent.
It's arctangent. Thank you. Okay, arctangent. And then finally, there's one more. If you take 1 over x square root of x squared minus 1 dx, this is going to be the arcsecant. X plus c. All right, so hopefully you have actually seen these formulas in Calc 1, and I encourage you to make sure you have these down, all right? Because these are sort of the building blocks for what we're going to be doing in terms of integration in this class. So you should know all these kind of by heart, okay? All right, good. Any questions up until this point?
Yeah, I have a question.
Okay, go ahead.
But it's an unrelated topic. So how do you pronounce your name? Is it Nakano?
Nakano, yes.
Okay, so I'll just call you Professor Nakano.
Okay, thank you.
Thank you.
Okay, so now that we have, so these are sort of like our ingredients that we're going to use. And what we're going to do is we're going to take various integrals and we're going to do various tricks, and we're going to actually try to sort of convert them into problems that we can actually solve by using these types of formulas. All right, so the first technique is probably something that you have seen before, and this is called integration by substitution. All right. Okay, so now we talked about this a little bit. So if I have a function which is the composition of two functions, f of x and g of x. By the chain rule, when you take the derivative, what do? You take the derivative of the outside function, keeping the inside function the same, and then you take the derivative of the outside function like that, or inside function, sorry. Okay, so this is the chain rule. Okay, so the idea with integration by substitution is that a lot of integrals are sort of disguised as unraveling the chain rule. So what I can do is I could start with an antiderivative, which is of the form f prime of g of x, g prime of x, and I can unravel it. So if you go backwards in the process, this is going to be f of g of x plus c, right? So sometimes the chain rule is actually hidden inside the antiderivative. And what we want to do is we want to unravel the chain rule in a systematic way so that we can solve for the antiderivative. Okay. All right. So we'll do a bunch of examples and you'll kind of see how this works in a moment. So let me put down two guidelines that you may want to consider using. So the idea is to try to make okay, so I'll be a little vague here. Something in which u prime will cancel the terms involving, let's say, x. So you're gonna make u be part of the integral, and then what you'll do is you'll take the derivative, and you want the derivative to cancel with the rest of the stuff. Okay. So the other guideline is to try, if not, try to see if changing x in terms of u will make the integration simpler. So I'll go over an example of that in a moment too. All right. So I think these principles or guidelines are just best tested on examples. Okay, so we're going to do tons of examples, and hopefully by the time we've done like, one or two examples, you'll kind of get the hang of doing this integration by substitution. You've probably seen it before, so let's start on some examples. Very, very concrete examples. Okay, so the first example. So I have x squared plus 1 squared and 2x dx. Okay, now I can solve this problem by just multiplying everything out and then integrating term by term. But I don't want to do that in this case. So the first thing I'm going to notice is that I can do a substitution. I could substitute for u squared plus 1, and the derivative is going to be 2x. And that'll actually cancel out with the rest of the terms. So let's do this sort of systematically. So let's say I take u to be equal to x squared plus 1. Okay. So if I take the derivative, which is du dx, this is going to be 2x. Okay, so in particular, this du part is going to be 2x dx. All right, so let me do this side. This is going to be u squared. And then the 2x dx part is just going to be du. right? Okay, so notice that this is very clean because I was able to transform by just using a substitution something involving x in terms of something involving just u itself. Okay, so it actually was kind of disguised, in terms of the chain rule via this formula. All right, now this integral is much easier, right? We can just solve this. So we know how to do this. So what is the antiderivative of u squared?
Cubed over 3 plus c.
Good. And now for the indefinite integrals, I want to substitute back in. So for indefinite integrals, substitute x back in. Okay, so I have a formula for u up here. So I'll substitute that back in. Okay, and that I'm done. And that's it. Any questions on this problem? Okay, good. So let's try another one. So we take the antiderivative of cosine 17x dx. All right, now, maybe you can just do this in your head. But let me just systematically go through this using a u substitution. All right, so what do you think we should make u equal to here?
17x.
Good. And we do the same procedure. Du dx is equal to 17. Okay, so this is the integral of cosine u, and dx is equal to du over 17. Okay, we can just substitute in the dx part. So this is du over 17. Okay, so this is going to be 1 over 17, integral of cosine u du. What is the antiderivative of cosine?
Sine.
Sine, good.
Sorry.
Great. And then what we can do is we get to substitute the 17x back in. So 17. Okay. It's as easy as that. Okay, any questions? All right, now I'm going to give you a problem which is slightly trickier, but we just use our imaginations a little bit. Okay. So I have the integral of x times 2x minus 1 here. And so I want to be able to, sort of figure this antiderivative out, right? Now, we can't really multiply things inside. I mean, it's not going to work. And so, you sort of look at this thing and you sort of say to yourself, what's giving me the troubles? And so you say, well, maybe the thing that's giving me the troubles is the thing inside the square root. So maybe we should make that simpler. All right, so let's try doing that. So u will be just 2x minus 1. Okay, so let me just write this out. So I still have the x in here, and I have the square root of u, and I have a dx here. All right, and if I take du dx, that's going to just be 2. Okay, so I can solve for the dx part. So the dx part is just going to be du over 2. Okay. Now, I still have the x lying around. It wasn't canceled out like the other problems, right? So what should I do now?
You can use that first equation.
Yeah,
uh,
that's
substitute.
right. Yeah, exactly. I think I heard from several people. So I want to use that first equation and then I'm going to just solve for x. So I want to use this one over here and let's just solve for x. So that's u plus 1 is equal to 2x. So x is going to be equal to u plus 1 over 2. Okay. So I get here, I get u plus 1 over 4 times the square root of u du. So let me just clean up a little bit. So here's a 1/4 u plus 1 square root of u du. All right. Okay. Now,
Question, comment?
what? Sorry. So let's pause for a second. A question?
Yeah, can you explain why it went from u plus 1 over 2 to u plus 1 over 4?
Oh, I combined the 1/2 over the du. There's a 2 under the du, which is 2. So you get 2 times 2, that's 4. Right here.
Thank you.
Does that make sense? Yeah, okay. All right. So that I just pulled the 4 out. Okay. All right, now let's do a little comparison shopping. All right. So you look at the top thing over here and you look at this one. All right, now what makes the bottom one better than the top one? Can I find the antiderivative for the one involving u? Yes, no?
Yes.
Yeah, so how do I find the antiderivative for this?
You just put it into.
Yeah, you just multiply it. That's right. That's exactly what you do. So you take 1/2, 1/4, I'm sorry. So u times, notice, so the point is that you can use the distributive law here in a very effective way, right? So you take u times u to the 1/2, that's u to the 3/2, okay, plus u to the 1/2. So you can just distribute through like this. And now I could just use the formula that I've had before, and then I'm good to go. So let's do that. So it's 1/4, and this is u. Remember, add 1 to the power. Okay, so that's 5/2. Divide by the new power times 5/2. Add 1 to the power. Divide by the new power. Okay, and so now I get 1/4, and I get 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. Okay, and I don't know, I can multiply everything through if I want. So I get 1/10 u to the 5/2 plus 2/12, that's 1/6 u to the 3/2 plus c. And then you want to go back to this, the u. So u is equal to 2x minus 1, substitute it back in, and then I'm done.
I have a question.
Yeah, go ahead.
So how did you go from u plus 1 to u to 3/2? Like for the third step down to the fourth step down? So I'm from the top.
From here to here. Yeah, so if you have 5/2 in the denominator, that becomes 2/5.
Well, no, I'm talking about u to 3/2 plus u to the 1/2 du. I don't know how you got to that. Like you had u plus 1 times the square root of u, and then you went to that.
Oh, you mean from here to here, you're saying?
Yeah,
So I just used the rule that I had back, like right here. Right, I'm using this rule here,
okay,
right? You add 1 to the power and you divide by the new power.
okay,
That's how you
okay,
find the antiderivative of any like x to some power,
alright,
okay?
Yep.
So that's what I did. Add 1 to 3 halves, divide by the new power. Yeah. All right, now we're good. So we can actually put in the 2x minus 1 in here. So 1/10, 2x minus 1 to the 5 halves plus 1/6, 2x minus 1 to the 3 halves plus c.
Professor McConnell. I have a
Yes.
question. So I guess in the second equation where it starts with the 1/4,
Second equation.
the second one where it starts with 1/4.
Okay, right here. Yeah.
So can you explain how you went from u plus 1 to u to the 3 halves?
Yeah, I just multiplied it in, right? Because, I mean, if I take, let me just do it down here. So I take u plus 1 square root of u. If you want to think of it this way, it's u plus 1 times u to the 1/2, right? And so now I'm going to distribute in. So this is u to the 3 halves plus u to the 1/2.
Got it. Thank you.
Okay. So that's what I'm doing. And notice you can't do that when you start out with. Because there's all this junk under the square root. So I needed to simplify what was under the square root in order to apply the distributive law. That's the whole point about this problem. And it's a little bit of a trick, to be able to do this, but like if you see this kind of thing on homework, for example, now you'll know how to do it. So. Okay, other questions? Okay, so we're just gonna do a bunch of examples because I think, seeing is actually being able to do things, so. So secant x, square root of tan x dx. Okay, so I have this integral antiderivative, and now what should I do? First of all, is there something which is kind of bothering us that we may want to substitute for? If it is, can we get it to cancel out nicely with, something else?
Tangent of x.
Yeah. Okay, so someone said tangent of x, and that is good. Someone else have a question on this?
No, I was just answering the question.
Okay, thanks. All right, great. So you guys, tangent x is a good candidate. So let's take the derivative, which we know is secant of x, right? And now we can do what we need to do. So here I have secant of x, square root of u. Now dx here is going to be equal to du over secant squared of x. Okay, so now I have du over secant squared of x. And conveniently, because the problem is rigged, those two cancel out. So then I have the integral of 1 over square root of u du. So now I'm just going to rewrite this as u to the minus 1/2 du. What's the antiderivative of u to the minus 1/2? What do we do?
Is it 2 times u
Yeah,
squared
so
of u?
right, so add 1 to the power, which will give you u to the 1/2, divide by the new power, and then you could just make this 2, right? Like that. I just put in the steps to make sure it's clear. All right, and then what do we do after this? What should we do?
Plug tangent back in.
Okay, very good. So we plug the tangent back in. And that's it. We're done. Okay, so now this is all, I have done all this for definite integral, I mean indefinite integrals. Okay, so every example I had involved an indefinite integral. And now I want to do a substitution involving a definite integral. Okay, so maybe I'll even say this. So this is substitution using a definite integral. Okay, so this is slightly different a procedure. The principles are the same, but some of the procedural parts are slightly different. Okay, so let me again give you an example. All right, so here's the example. So I want to integrate from 0 to the square root of pi of 2x cosine to the 1/2 x squared dx. Okay, great. Now, in this problem, we can see what we want to do. Well, we want to get rid of that 1/2 x squared inside the cosine. That's giving us problems. So let's see if we can do something with that. So when I make this du dx, I'm just going to get x again, right? I just take the derivative, right? Now, one thing to understand is that everything here is in the x language. And when I do this substitution, I need to go from the x language to the u language. Okay, so that means the bounds are also in terms of x. So what are the bounds in terms of u now? So if x is 0, what is u?
It's also
1,
0.
also 0. So when x is going to be the square root of pi, what is u going to be?
Pi over 2.
Pi over 2. Okay, so I have to change the bounds in terms of u, right? You don't want to translate half the language, right? You want to translate the whole language.
Why is it pi over 2?
Because I just plug in the square root of pi into this formula over here. Right?
Oh.
Yeah, okay. So remember,
Okay.
this is like, the formula is like the interpreter, right? I mean, the
Wait,
formula.
the formula, is it the formula like next to the integral? 2x cosine of,
The formula is the thing that's circled right here.
oh, okay.
That allows you to translate back and forth, okay? All
Got
right,
it.
now I just have the 2x over here. I have a cosine u, and dx is going to be equal to x, right? So dx is du over x, right? So the x's will cancel out. Okay, get rid of the x's, and I get 2 integral 0 to pi over 2 of cosine u du. Okay. So now we just do what we need to do. This is sine of u, and we're going to evaluate from 0 to pi over 2. Okay. Now I don't need to go back to x again. That's so with the indefinite integral, I had to resubstitute x back in. But here, everything's already in the u language, so we could just forget about x. Okay. So we could just plug in. So that's 2 sine of pi over 2 minus 2 times sine of 0 using the fundamental theorem of calculus. What's the sine of pi over 2? 1, okay. Sine of 0 is 0. So our answer is just 2. Okay, so again, with a definite integral, once you've done the substitution and you've eliminated the x, you don't have to go back to x again. You can just evaluate, no problems. With the indefinite integral, once you have this in terms of u, just u alone plus c, then you have to substitute back in. Okay, is that clear? How we did this, how some of the subtleties and the differences? We'll do more examples later on, clearly. Okay. Great. Okay, so it looks like we are sort of near the end of class, and so are there any questions on these procedures before we conclude? Let me go check the chat too. Okay. Oh, lots of answers on the chat. No questions. It's good. Okay, so if not, thank you very much again. I wish you a happy weekend, and we'll see you back in Athens on Monday. Okay, bye-bye.
Thank you.
Okay, welcome.
Thank you.